Okay guys, let's finish 10.1. There's one page left and go on to 10.2 where we actually do some problems. Conclusions to hypothesis testing. When you're writing a conclusion, even though we talked about you always either reject or don't reject the null hypothesis, your conclusion statement is always going to talk about your alternative hypothesis, not the null hypothesis. So, because you're testing your alternative hypothesis, it's the statement you made, so it's important that the statement you made is judged based on your findings. So according to a study published in March 2006, this is the phone call problem again. Researcher believes that the mean length of the call has increased since it was 3.25 minutes per call then. Suppose your evidence indicates the null hypothesis should be rejected. If your null hypothesis should be rejected, that means there is sufficient evidence, since you rejected, to conclude the mean length of the phone call of a cell phone is greater than 3.25 minutes. Notice that this was our alternative hypothesis. Now, when you do reject something, you usually say there is sufficient evidence to conclude that. Normally, I will let you just say there is and then sufficient evidence to conclude that. If you're ever writing this out on paper, that would have been enough for me. And then state the alternative hypothesis. Now, suppose the sample evidence indicated the null hypothesis should not be rejected. State the wording of the conclusion. Again, we talk about the alternative hypothesis, so if there isn't evidence, then there is not sufficient evidence to conclude that. Same SCTCT. The mean length of the phone call on cell phone is greater than 3.25 minutes. So you either accept or you reject or you do not reject the null hypothesis, but then when you write your conclusion, it'll talk about your alternative hypothesis there. And that's all for 10.1, so let's go straight into 10.2. So hypothesis testing for a population proportion. Now there are three ways to do this: the classical approach, the p-value approach, and the confidence interval approach. We are not going to use the confidence interval approach. The reason for that is it only works for two-tailed tests, and if you learn two other ways to do it, there's no reason to have a third way that doesn't always work. So the classical approach is first, your step one is to determine the null and alternative hypothesis. And hypotheses can be structured in one of the three ways we talked about in 10.1. You have to select a level of significance that'll be based on the problem. Depends on the seriousness of a type 1 error. It'll be done by the researcher, so it's really you just finding it in the problem, in the wording. You compute the test statistic, which is the z-score. And we use p naught in computing the standard error rather than p hat. It's because we're testing a hypothesis. Therefore, it's the null hypothesis that's assumed to be true. So you always use the null hypothesis proportion for your statistic, and then you use table 5 to determine the critical value. So when you have a two-tailed test, this is where you have to split your region in half, because basically if you say 5% of the time, that's your alpha. So you have an alpha of 5%, and you're doing a two-tailed test. That means you're splitting your 5% into two pieces. You're putting some of your eggs in the lower basket, some of your eggs in the upper basket. Whereas if you're just doing a left-tailed or right-tailed test, you're putting all of your eggs in only a single basket, which means you have more room to figure out an outlier when you're sure on one side or the other. However, if you find one that's way off to the left and you're only doing a right-tailed test, you made it where it's impossible for you to draw your conclusion there. You would have to do a new test. Now you compare the critical value with the test statistic. If you drew a picture of it, if it falls within the critical region, that's if it falls on the outsides in those shaded areas, then you reject the null hypothesis. That's evidence that the null can be rejected. However, if it falls in like the white areas in the pictures, the inside, the center, then you do not reject, and then you would write your conclusion. So that's a lot, so let's actually do a problem and see how this works. Now remember, it's a test hypothesis regarding the population proportion. We can only use these steps if the sample is obtained randomly, and we need n times p times 1 minus p to be greater than or equal to 10, and the sample values need to be independent of each other. So let's get this going. In 2001, 23% of American university undergraduate students had at least one tattoo. A health practitioner suspects that the percentage has changed since then. She obtains a simple random sample of 1,025 undergrad students and finds that 255 have at least one tattoo. Is this sufficient evidence to conclude the proportion is different than 0.23 at the 0.05 significance level? So that's our alpha. Use the classical approach. Okay, she said it's different, so that's going to be a not equals to. So the null hypothesis was our old data set as p equals 0.23. She thinks it's different. It's changed since then. And she wants it at the alpha equals 0.5. That's the significance level. Now, what does that mean, the alpha significance level? That means it'll affect our critical region. So that means she wants 5% of the data on the outside. Because it's a not equal to, that 5% is split into 2.5%, 2.5 pieces on either side. And this will affect our critical value. Now we know from our confidence intervals, this critical value should be 1.96 or negative 1.96. That's exactly the same as a 95% confidence interval critical value. So the same critical values that we used before are still common in this section. And it says your test statistic is p hat minus p naught. So the R value minus the null hypothesis over the standard deviation. What is R value? We need to take 255 and divide it by that 1,025. What percentage did she get in her sample? And this is 0.249. Now, when I plug this all in here, I get 0.249 minus my null hypothesis number, 0.23, over the square root. This is our standard deviation. So I'm going to calculate my standard deviation over here instead of putting it all in one equation. This makes it harder to make sure you get the right answer. That'd be 0.23 times 1 minus 0.23, so that's 0.77, all over however many people we sampled, 1,025. This is approximately 0.013 in the calculator. So this whole thing, 0.2949 minus 0.23, which is 0.019, is divided by 0.013. It's approximately 1.45. Now, how does this help us? If we look at the picture, again, our critical region is the outsides, right? It's less than negative 1.96 or greater than positive 1.96 from our picture above. Where is 1.45 in there? It's greater than halfway, right? But not quite to the 1.46. So is it in the shaded region? No, because 1.45 is less than 1.96. In order to have evidence to reject, we need to be in the shaded region. Since it's not in the shaded region, we say we do not reject H naught, because it's not in the shaded region. Since we do not reject H naught, that means there is not sufficient evidence to conclude that the proportion of undergraduates who have at least one tattoo is different from 0.23. And we will continue in the next video.